Does this make sense to you? Yes.
Can you explain one more time how you define the XX? Like,
Oh, how I define the
Yeah.
XX, right. So let me first write it carefully. This is XX. So every normal stress is going to be described by two indices. Okay. The first index is the direction of the normal force itself, or the normal stress. Okay, so which is going to be the x direction, right? Because the normal force is pointing in the x direction. The second index is going to be the area normal, the direction of the area normal. That is the direction of a vector that is normal to the cross-sectional area, and that is going to be in the x direction. So that's why I have sigma xx. So which means sigma yy is, if I say sigma average yy, is it 0 or not? There are no normal forces acting in the y direction in this case, right? So sigma yy is 0, sigma zz is also 0 in this particular case. Okay? I'm going to take off this particular panel here. Now watch this. Yes, yes, question.
I just have a quick question. So for like the sigma average XX, does it matter if it's positive or negative? Because it kind of looks like one x is positive and then that would make the other x negative. Does that matter? Is it just like what point?
Right, absolutely good, great point. Positive or negative is given by whether it is tensile or compressed. Right. So these, you don't need to account for the directionality because as you rightly pointed out, the x-axis positive is into the page, but the area normal is out. And the direction of the normal force is along the negative as well. So we don't bother about the signs on these. The totality of the signs is captured by saying whether it is tensile or compressed. Okay. And I'm going to mark this point A and point B here. So this is A. This is some point B. So what is the average normal stress at the point A? It is the same as the average normal stress at B, and they're both put together equal to F by 2 W. Yes.
So,
Those are the normal forces. Forces that are normal to a cross section. Forces that are perpendicular to a cross section. Okay. Is everything making sense to everybody? Alright. Then I go to the calculation of the effect of the bending moment. Okay, so we have seen the formula for this. What's the effect of M max is to cause a bending stress. The basic formula is the following. Sigma bending. Always use the formula the way we derived it. It is minus M y by I neutral axis. Extremely important to understand this is the formula. And everything has a precise purpose here. The bending moment M is according to the sign convention, which means if my bending moment I am using in the problem is negative, I am going to substitute this entire value minus F times L as the value of capital A, so that I get positive. Okay? Now I am going to draw the cross section. Once again, we won't be doing this for each and every problem, and you don't need to do it either. This is just for our understanding. Okay, so here is my cross section. I'm going to label points A and B here. Centroid. This is my y-axis. This is the z-axis. I'm going to do the calculation of the bending stress at point A. So sigma A bending. X-axis is into the page. Right? So what is the direction of the bending stress? Once again, the indices I and I. The second index is the area normal, so the second index is always easy to write, so the second index is x. The direction of the bending stress is what? Is it x or y or z?
Z.
If I'm looking at how the cross section is bent, look at this here. Once again, this is the cross section. The palm of my hand is my cross section. Just by the way the moment is drawn, it looks as if I slice my palm and the moment is trying to rotate my palm about the sliced point, it is trying to push things on the top into the page, push things at the bottom out of the page. Right? So which means that the totality of the direction of the bending stresses is going to be along the direction normal to the cross section. Okay, so this is going to be in the x direction. So this is also x. Does this make sense to everyone? Question?
So you're saying that the axis on the z-axis, but it's acting like it's forcing the forces to the x-axis.
It is forcing the fibers on the top and the bottom to be either pushed or pulled out of the cross section. If I do the calculations, M max is minus F times L, so this is first of all minus FL, which is the moment. Y is the distance of the point A from the neutral axis, so this is the neutral axis. This is Y for the point A. Y for the point B. Y for the point A is positive because I'm looking above the neutral axis. Plus T. Y for point B is minus T. Does this make sense to everybody? Okay. And so if I do the substitution, this is going to be plus T divided by I about the neutral axis we just calculated, 2 by 3. That will be 3. L is 20 times T. Do the substitution, so I end up with the following. So sigma A bending is, I have 20 times T, so I get a T square. This becomes a 30 by 30 times 3 times 2, so 60 by 2, so that's 15, 30 F by WT. Okay, so if you do the calculations, you'll end up getting that to be the answer. This is 10 times, 20 times T. Okay, so I have a factor of 20. This is 3 in the denominator of a denominator comes up, becomes 20 times 3 divided by 2. So that's 30 F by omega W times T. Is it tensile or compressive? I get a positive value, so the stress is tensile. Do I need to do any calculations to find the stress at point B? It is exactly the mirror image of what's happening at point A. But then, if I do the calculations, if the top half is now in tension, so all of these are now in tension, the bottom half is going to be in compression. Does this make sense to you? If you want, if this negative sign is bothering you, you can change the direction of the negative sign and say, okay, hey, really, this is F times L acting this way. So if this were my palm, the moment is acting such that it's trying to pull the top of my palm out of the board, push the bottom of my palm into the board. The direction that is perpendicular to the board is the Z X direction. The direction of the area normal is also the X direction. So this is XX. The top points are in tension. The bottom points are in compression. What is the stress at any point on the neutral axis due to the bending stress?
0.
It has to be 0. Okay. So sigma B bending XX is minus 30F by WT. Right, and you can also draw the direction of the arrow, so this is in tension, this is in compression. Okay, so this is C, S is tension. Any questions so far, please? Yes. Correct. Do you see why it happens? Okay. It's important that we understand it for a cross-section of this simplicity. The rectangular cross-section is the simplest cross-section, because we're going to jack it up as we go further in the next week and so on, where you'll start looking at L sections, T sections, and whatnot. So if you have any questions, please let me know. Please stop me before I go further. I have a question for you all. If the stress at point A due to the normal force is F by 2W times C, and the stress at point A due to the bending moment is 30 FWT, what is the total normal stress at the point A? It's going to be the sum of whatever is the bending stress due to the normal force, and whatever is the axial stress due to the normal force, and whatever is the bending stress due to the bending moment. In this case, at point A, I am in tension. At all points in the cross section, I am in tension. So if I add the effects up, the total normal stress at point A, sigma A XX, is the following. I'm going to erase some portions of the chalkboard here. Yes, yes. All of these will be posted for you. Thank you. Okay, so sigma A XX is sigma A average. I call it average, so let's call it as average. Sigma A average in the XX, and then sigma A bending in the XX direction. It's kind of weird to call it as direction, right? Because I have two indices. So stress is actually called as a tensor, and a tensor is a quantity which essentially requires more than one particular index to prescribe its behavior. We will go into it, as I said at the beginning of the semester. We are going to talk about tensors very soon. So just bear with me for the time being. This might look a little uncomfortable. We will see the basis for this. Okay? I just add this up. So this is 0.5 F by WT. That's 30, so 30.5. Sigma A. XX is and the cumulative effect is tension. And because this is in tension, that is in tension, they add up and give me something that is in tension as well. Does this make sense to everybody? Okay, this is half, so 0.5 F by WT. This is 30 F by WT. 30 plus 0.5 is 30.5. I do the same thing for B. Watch what I'm doing. Sigma B XX is sigma B average plus, watch this, plus sigma B bending. Make sense to everybody? Sigma B due to bending is minus 30 F by WT. Sigma B due to the average normal stress is 0.5 F by WT. So this is 0.5 minus 30 F by WT, which means that I'm going to get a negative value. So the totality of the stress state at point B is a compressive normal stress. Okay, so sigma B XX 629.5 FY WT. If you put the negative sign, don't say compression. If you don't put the negative sign, say it is compression. Don't double count. Okay? So this is one. This is the other. And I want to see if there are any questions so far. Please, yes, question.
I got a quick question about the indices. What is an example when it's not XX, YY, or
Shear stress.
the shear stress is?
Right,
Okay.
right.
It's like your normal stress is always perpendicular to
Absolutely.
the area. Okay.
So you see, so there is going to be a shear stress due to the shear force. Right?
Yeah.
The direction of the force and the shear stress is the y.
Mm-hmm.
The area normal is x.
Got it.
So if I write the index for the shear stress, it's going to be tau xy
Okay.
or tau yx in this case. Okay. So that's exactly what we're going to do.
So for normal, it's always.
It's always
XX.
either sigma
Okay.
xx, yy, or zz.
Gotcha.
Absolutely. All right. I'm going to get rid of this panel here. Okay. And then start my shear stress calculations. I'm just going to gloss over the details of what we did last time. If you go to the lectures that I posted, you'll see my derivations there, so I'm not going to derive everything again. If I have a cross section of width W, this is the neutral axis, the total height is T, and T from the neutral axis. If the direction of my shear force is, let's say, up. Okay, so this is the direction of my shear force. If I am interested in finding the shear stress at some point on the cross section, which is located at the distance y from the cross section, the first thing I do is I draw a line parallel to the neutral axis. Okay, this line is parallel to the neutral axis. Starts from one end of the cross section, goes all the way to the other end, and intersects the point on this cross section. Okay? And I label this distance as y. Okay, so this is some point, let's call this point as some point D. To calculate the shear stress, we use the formula VQ by IT. Now, transverse is the name for the shear stress because it is transverse to the cross section. Transverse meaning parallel to the cross section. Normal forces have a name normal because they are perpendicular to the cross section. Okay, so transverse, normal. This is VQ by IT. Neutral axis, and T, I said T tau, just to distinguish it from the thickness of the cross section itself. So T tau is the total length of this line starting from one end to the other, passing to the point of interest. So for me, T tau is equal to W for the point I'm interested in. Q, I take up either the area above the point or below the point. Okay, after drawing this line, I take up either the area above or below. It is completely fine to do either. You're going to see this in a homework problem where you will do either and you'll get the same answer. I will call this area as A prime. And I locate the centroid of this area. In this case, it is fairly straightforward. It is just the center of the area. We call that as C prime. And I calculate the distance from the neutral axis all the way to the centroid C prime as y bar prime. Watch this, I'm looking at a distance, not a magnitude, not a signed quantity, it is just the magnitude that I'm looking at. So this is going to be y bar prime. From the previous lecture, Q is A prime multiplied by y bar prime. And A prime is fairly straightforward, so this is minus y, t plus y divided by 2. Okay, so this is all from the previous lecture. A plus b times a minus b is a square minus b square. So that tau, I'm going to give indices now. We're typically going to say tau is tau ij, or ji, I'm sorry. Okay, those are the indices for shear stress. The second index is the same as the area normal that we used for the normal stresses. So the second index in this particular case is going to be the x-axis. The first index j represents the direction of the shear force. In our calculation, the shear force is pointing along the positive y direction. Okay, so this is going to be yx. And if I calculate this, this will end up being the following. So I'm going to have V, in our case, V is equal to F. This is V. So this is F times W times t minus y times t plus y is t square minus y square. That's a factor of a half. I neutral axis. This is divided by 2. 2 by 3. WTQ multiplied by t suffix tau, which is equal to W. Am I making sense to everybody? This is exactly what we did last time. Okay, I'm just borrowing ideas from there. The W in the denominator and the numerator cancels out. That's gone from me. I'm going to clear up the board here for a little bit. Look at this. I'm now going to calculate the transverse shear stress at point A. This is at some arbitrary point, right? And one more thing you want to keep in mind, this is a y square. So whether my y is calculated above or below the neutral axis, y square is just going to be a positive quantity. So tau transverse at point A what's it going to be equal to? At point A, what is the value of y? Is equal to t, right? Because I'm starting from the neutral axis going all the way up to point A, so the value of y is equal to t. If I take that t and I substitute that here, what do I end up getting? Get 0. If I do the same thing at point B, what will I end up getting? It will still be 0 because even though my distance from the neutral axis is a negative distance, okay, so if I substitute yb as minus t, I'm just doing the substitutions in this particular formula, you will see that it's y square, so that's t square minus t square is still 0, so this is still 0, this is fantastic. My stress is 0 at the top, 0 at the bottom, so I can choose any point at the top. My shear stress, transverse shear stress is 0. Any point at the bottom of a cross section, my transverse shear stress is 0. So when somebody comes and asks you, hey, here is my cross section, somebody is telling me that the maximum stress due to shear is occurring at the top and the bottom, is this correct or not? That is a whole load of garbage. Okay? So that's wrong. But the other question is, okay, where is this a maximum? Where do you think this could be a maximum? Has to be at the center, right? Because when y is 0 is when this becomes a maximum. If y is 0, I am sitting at the neutral axis. So the maximum shear stress due to the transverse shear occurs at the neutral axis. So I'm going to write down all these thoughts. I'm going to get rid of this panel here. Okay? I have a few more minutes, 1 more minute. First of all, the distribution of the shear stress is a quadratic because of the fact that this is a y square. Okay, so tau transverse is maximum at the neutral axis. Maximum at any point on the neutral axis. I take any point on the neutral axis, the distance y is 0, so this is a maximum. Tau transverse is 0 at any point on the top and the bottom of the cross section. Of the cross section. And if I have to draw this as a stress distribution, that is my last thing for the day, it will be drawn along the face, along the cross section. The largest arrow will be pointing in the arrow direction of the shear force. So everywhere here. It will be a maximum. As I keep going up and down, the magnitude of these arrows will keep reducing. Okay? So it will become a little smaller here. Same story. As I keep going further up, it will get smaller and smaller. And you see that the length of this arrow signifies the magnitude of the shear stress. Largest at the neutral axis. As I keep going away from the neutral axis on both sides, the magnitude of the shear stress keeps reducing. Okay? So this is all I wanted to accomplish for the day. Thank you. I'm going to have a review session on Sunday afternoon at 1 p.m. via Zoom. If you can, please try to make it. Okay? Monday we will have lecture as usual.
I need to pick up some. My roommate's still recovering from his nail incident, so I'm gonna pick up some food.